Induced crystal G phase through intermolecular hydrogen bond constructed by p-n-Alkoxy Benzoic acids with Ortho-Toluamide, nOBA TMD. Abstract: a new series of supramolecular liquid crystals, nOBA TMD n equals 4 to 12, were synthesized with mesogenic p-n-Alkoxy Benzoic acids, nOBAS, and non-mesogenic Ortho-Toluamide, TMD, moieties. Intermolecular interaction between the proton donor, COOH, of nOBA and proton acceptor, O, of TMD results the hydrogen bond. Newly formed complexes are characterized by polarizing optical microscope and differential scanning calorimetry, along with the conformational studies of hydrogen bonding through vibrational spectroscopy, FTIR. The IR spectral study confirms that the formation of hydrogen bond between proton donor, COOH, of nOBA and proton acceptor, O, of TMD. The formation of hydrogen bond is attributed to the quenching of the nematic and smectic phase and inducement of crystal G phase in liquid crystal complex. A comparative study of phase abundance is presented with respect to the pure p-n-Alkoxy Benzoic acids, nOBA, and other hydrogen-bonded liquid crystal complexes of nOBAS. Keywords: supramolecular liquid crystals, intermolecular interactions, hydrogen bond differential scanning calorimetry, Fourier transform infrared spectroscopy. Introduction. Unique materials that have large number of applications in the field of engineering, technology, and medicine are liquid crystals 1 to 5. As these materials possess good number of applications, there is always vigorous research in developing novel liquid crystalline materials with different molecular structures and phases. Preparing novel liquid crystals involve various techniques like synthesizing using organic compounds and mixing two different compounds, metals, and halogenated compounds, etc. 6 to 9. In most of the cases, chemists keep keen observation on the synthesis of hydrogen bond 10 to 21, as well as p-n-Alkoxy benzoic acids 19. Among these novel liquid crystals, hydrogen-bonded liquid crystals have distinctive nature to show mesomorphic behavior due to their strong and directional nature in different types of interactions. 22. The alkoxy benzoic acids exhibit liquid crystalline nature. The same nature was observed in all hydrogen-bonded liquid crystals obtained from the combinations of mesogen and mesogen, non-mesogen and non-mesogen, mesogen and non-mesogen materials. The non-covalent interactions exhibit superficial effects on physical and thermal properties, i.e., mesomorphic behavior, and transition temperatures. 15. In the present article, a novel homologous series of liquid crystal complexes are prepared through the development of hydrogen bond between COOH of liquid crystal compounds p-n-Alkoxy benzoic acids when N equals 4TO12 and O of non-liquid crystalline compound Ortho-Toluamide, TMD. Fourier transform infrared, FTIR, spectroscopy is used to confirm the formation of hydrogen bonding, and the prepared complex's mesomorphism is characterized by polarizing optical microscope, POM, differential scanning calorimetry, DSC. 2. Experimental. The p-n-Alkoxy benzoic acid, 99% purity, and OTMD supplied by M/S Frinton, Inc., USA. Solvent pyridine from M/S Qualigens, India. The transition temperatures and phase variant of p-n-Alkoxy benzoic acid and corresponding hydrogen-bonded complexes were found from textural observations carried out using thermal optical polarizing microscope, MEOPTA, Drew 3, with a hot stage and HD Canon camera attachment. Methodology for sample cell preparation and observation of mesophase of the samples as a function of temperature has been given in 9,16, and 19. Phase transition temperatures were compared with temperatures of Perkin-Elmer diamond differential scanning calorimeter, DSC, at a scan rate of 20C/min and confirmed. The IR spectrum in solid state was recorded on FTIR, FTIR 5300, spectrometer, JASCO, Japan. Preparation of p-n-Alkoxy benzoic acid, nOBA Ortho-Toluamide, TMD, complexes, where N equals 4 to 12. Supramolecular hydrogen-bonded liquid crystalline complexes, namely, nOBA, TMD, where N equals 4 to 12, are prepared by the following procedure given in Scheme 1. Required amount of samples for synthesis are weighed on a single pan electronic balanced HONA make, ER180A with an accuracy of 0.01 mg. Equimolar, 1:1, ratio of nOBA and TMD are used for the preparation of liquid crystal complexes 4-OBA, TMD to 12-OBA TMD. Compounds are taken individually and mixed in the pyridine solvent, 20 ml. Thus the naturally existing dimeric forms of nOBA compounds with complementary hydrogen bond are converted into the monomeric form. Now the two solutions are mixed and kept under constant stirring at 800 C for 4 HRS. Then most of the pyridine is removed by vacuum distillation process. It means the resultant homogeneous mixture was reduced to almost dryness by removing the excess pyridine under a controlled vacuum filtration. The white crystalline product was dried and recrystallized from hot dichloromethane solution. The yielding is at about 85%. The entire process involved in synthesis of given liquid crystal complexes are shown in the form of chemical reaction as follows. Newly synthesized nOBA, TMD complexes are characterized by different thermal analysis techniques, POM and DSC. Structural characterization is done by the FTIR studies. Complexation of mesogenic nOBA and non-mesogenic TMD influences the thermal and phase behavior of pure mesogens. The resultant nOBA TMD complexes shows the interesting and completely novel phases which are not present in the pure samples. 3 Results and discussion. Characterization of novel homologous series of liquid crystal complexes nOBA TMD are explained in the preceding section. In detail, all the pure series of samples possess nematic phase and samples with n equals 712 additionally exhibit smectic C phase. It was observed that phase transition temperatures of all the complex samples were decreased compared to their pure counterparts. Astonishingly, nematic phase was quenched in the complexes n equals 4 to 6 and crystal G phase was induced in whole series of the samples and nematic phase also observed in complexes with n equals 7 to 12. As a representative case, nematic droplets and crystal G phases of 8-OBA TMD was shown in Figs 1 and 2. Quenching of old phases, inducement of new phases and change in transition temperatures in the prepared complexes were identified, which has helped us to conclude that certainly intermolecular hydrogen bond is formed between nOBA and TMD 23 to 26. Crystal G phase 27 consisting of molecules packed in different layers with long axis tilted with respect to normal layer planes characterized by C-centered monoclinic cell with tilt molecules having pseudo-hexagonal close packing 27. Thermal span of all the crystal G phases induced in complexes range is around 100 C 200 C, which is a remarkable feature of these samples. Thermal span of the nematic phase was reduced from the pure mesogens, nOBA. The phase transition temperatures recorded using thermal microscope was in good agreement with the recordings using DSC thermograms given in Table 1. As a representative case, DSC thermogram of 8-OBA, TMD was shown in Fig 3. A Fourier transform infrared spectroscopy, FTIR. The IR spectra of the p-n-Alkoxy Benzoic Acids, nOBA, Ortho-Toluamide, TMD, and their intermolecular H-bonded complexes were recorded both in solid, KBr, and dissolved, in chloroform, states at room temperature and was shown in Fig 4. The summaries of infrared frequencies along with their assignments were shown in Table 2. The IR spectra of TMD exhibit the strong characteristic absorption bands at 3369.0 cm1 for NH stretching along with, outplane bend, OPB modes of NH at 618.02 cm1 28,29 nOBA. TMD complexes show the absorption bands in the range of 620-698 cm1 for, NH, OPB modes. Strong intense bands due to CH mode of benzoic acid moiety in the range of 2954 to 2916 cm1, which supports the existence of nOBA moieties in monomeric form upon complexation. The stretching, bending vibrations involving the proton donating groups, NH2, and proton acceptor groups, OH, showed shifts in their absorption frequencies, confirms the formation of hydrogen bonding in liquid crystal complexes. TMD with proton accepting substituent COOH, the intramolecular H bond in TMD disturbs the symmetry of the amino group. Therefore, the formation of intermolecular H bond with acceptor substituent is formed by the free NH group. Stability of the hydrogen bonding is observed by IR peak shift of the in-plane bend, IPB, mode of NH and CH towards the higher frequency side. As a comparative study between the nOBA TMD16 and nOBA TMD, n equals 4 to 12, the data given in Table 3 reveals that in case of NH, IPB, there is a increased shift of 74 cm1 for nOBA TMD and 513 cm1 for nOBA 9HB. And also by comparing the FTIR spectra of nOBA TMD and nOBA TMD, the below table shows that nOBA TMD exhibits the 12 cm1 hypochromic shift in NH bond stretch and nOBA TMD shows 25 cm1 bathochromic shift with respect to the NH bond stretch respectively. From the below table 4 it is observed that the thermal span for alkali complexes is more than alkyl complexes, further that thermal stability is comparatively more in nOBA TMD complexes and is around 50 C. Crystal G phase is dominant in nOBA TMD complex and nOBA TMD series. Further, the mol stability for nOBA TMD complexes lie in between 250 C. Hence, nOBA TMD complexes are thermally and texturally more stable than nOBA TMD. For conclusion, a new series supramolecular hydrogen bonded liquid crystal complexes have been synthesized from p-n-Alkoxy Benzoic acid, nOBA, where n equals 4 to 12 and TMD. The crystal G phase induced in all the complexes, and threaded nematic phase is induced in 12 nOBA TMD compound. Hydrogen bond is established between the O group of the p-n-Alkoxy benzoic acid and NH group of TMD, leads to an orthorhombic arrangement of the molecules. Hence, the molecular packing was influenced by the intermolecular hydrogen bonding. Due to this influence in each layer of the molecule of nOBA, an arrangement was created like head to tail and TMD as an adjacent molecule, a condition which induce crystal G mesomorphism. Acknowledgements. 1 of the author, SSS, is grateful to University Grants Commission for providing BSR Faculty Fellowship No. F.18-1/2011, BSR, dated April 1, 2017. The authors also gratefully acknowledge University Grants Commission Departmental Special Assistance Program at Level I Program No. F.530/1/DSA January 2015. SAP 1, dated May 12, 2015.